Hello. Today I will be talking about our work in the area of vapor absorption refrigeration systems. Refrigeration accounts for about 15% of the world's electricity consumed, and this is expected to grow as the demand increases. Refrigeration systems are a key contributor to global warming, both from the perspective of the greenhouse gases that are emitted due to the associated electricity use and the release of refrigerants which have very high global warming potential, sometimes a few orders of magnitude more than CO2. Most of today's cooling is provided by systems that operate on the vapor compression cycle. A schematic is here. The vapor compression cycle has a key component that is the electrically driven compressor. However, an alternate exists, and that is the vapor absorption cycle. In this, the compressor is now replaced by a set of heat exchangers and a pump, and what this does is this allows you to provide refrigeration by using thermal energy as the primary input. The second advantage is that these cycles often use working fluids that have zero global warming potential. The versatility of these systems is that they can use different heat sources. It can be solar energy, it can be recovered waste heat, or it can be even natural gas driven. These absorption systems can not only provide cooling, but space heating, water heating, and we have also been exploring the idea of using absorption for water purification as well, about which you'll hear more in a future project. So we envision a paradigm shift, I would say, in the way that we consume energy right now. Today, most of the energy is generated centrally, from which you transmit it across long distances, and they're consumed at the user location, and this encounters a lot of losses. We envision a world where each building has its own modular thermal hub, which is based on an absorption system, and that can provide all the thermal needs from your cooling, space conditioning, heating, water heating, and water purification by just using solar heat. And this will demonstrate a near lossless energy conversion on site. As you saw, absorption systems use a few extra components that make it very hard to build compact absorption systems. At STSL, we have looked at the idea of component miniaturization and integration to be able to develop compact absorption systems. One of our first work involved this, where we essentially photochemically etched all the components of an absorption heat pump on a single sheet of stainless steel. So there is the desorber, the absorber, the condenser, and all of the components on a single sheet. By putting two of these together, one for the working fluid, one for the coupling fluid, we have a small absorption heat pump that can give you a few tens of watts of cooling. In order to scale up, we put a few of these pairs together, bonded them, and what we have here is a 300 watt cooling capacity absorption heat pump. This is smaller than your heat transfer textbook. So this was a proof of concept to demonstrate that we can really achieve very high efficiencies in absorption systems in very compact volumes. In addition to this, at STSL, we have done extensive research to understand the fluid flow, the heat and mass transfer in these micro-scale geometries to be able to then transfer these learnings of the phenomena at the component and the system level. Behind me is a 3-ton, which is a 10.5 kilowatt cooling capacity absorption system that is driven by simulated waste heat. This system has a performance metric, that is the COP, which is the ratio of the cooling load to the amount of heat that is being input into the system, of about 0.7, and this can operate at ambient conditions as high as 45 degrees C. Now let's look at some of the other prototypes developed at STSL. What we have here is a 3.5 kilowatt cooling capacity absorption heat pump that is driven by natural gas. The core innovation again is the use of these microchannel heat and mass exchangers that have helped us to put all the absorption components in a very compact form, and it occupies less than 30% of the overall volume of this prototype. The prototype also has advanced control algorithms and has demonstrated autonomous operation. In addition to this, we have also developed a 7 kilowatt cooling capacity system that is again driven by natural gas and is well suited for residential applications. The other prototype I want to talk to you about is a completely air-coupled unit that uses waste heat from the diesel engine exhaust stream and provides cooling at extremely high ambient conditions like 125 Fahrenheit or 52 degrees Celsius. These are conditions typically observed in forward operating bases. So the last prototype I want to show you all is this absorption-based heat pump water heater. As you can see, this is designed to be able to retrofit on any commercial water tank. And what you might know that the electrical resistive heaters can give you an efficiency of 1 at best. What this system does, it has a COP of 1.73, which means for every joule of heat that you put into the absorption system, it puts in 1.7 joules of heat into the water tank. So what we've seen here is that we've developed a variety of prototypes for a variety of applications using a variety of heat sources. And this really demonstrates the versatility of absorption-based heat pumps.